And the two milk powders we're talking about are skim milk powder and whole milk powder. And we were talking about, during the production of skim milk powder, there's a specific step which involves the application of heat, and the heat modifies the proteins in the system. And depending on the time-temperature combination that you give the skim milk, you can produce different types of functionality in the final powder. So on the table up here, we have lots of different time-temperature combinations, but basically what you need to remember is that we've broadly 3 types of skim milk powder. I know there's more of them listed up here, but for your purposes, you can consider the 3 main types of heat-classified milk powders to be low heat, medium heat, and high heat. And as we go from low to medium to high, the intensity of the heat treatment increases. And as the intensity of the heat treatment increases, we have more denaturation of whey proteins. And when the whey proteins denature in the system, a large proportion of them interact with the casein micelle. So we said that in milk, the casein micelle has this specific hairy layer, and this provides the casein micelle with some good functional properties, namely stability to heating. So the casein micelle naturally in milk is really good at remaining stable to heating. And one of the reasons for that is that it has this extended physical layer at the surface that protects casein micelles from coagulation during heating. And what we're doing here when we increase the intensity of heat treatment and we denature the whey proteins is we're attaching the whey proteins to that protective surface. And in effect, we're increasing the size of the stabilizing layer. So this step is called preheating during the production of a milk powder. It's got quite a boring name, but it serves a very important functional purpose for the final powder. So as we said the last day, when we go to the low heat varieties, the temperature time combinations they can be exposed to are very close to what you're familiar with in terms of pasteurization temperatures. So normally when milk is pasteurized, drinking milk, the temperature is sufficiently high to kill bacteria, but it's not sufficiently high to denature whey proteins. So in most cases when you're processing drinking milk, you're trying to minimize these types of changes to the protein structure. But oftentimes for specific applications of these powders, there's a desire to promote whey protein denaturation and attachment to the casein micelle surface. So we said that these different types of heat classified powder can then be useful in certain applications. And again, there's a lot of them listed up here, and I'm sure these different powders work wonderfully in these different applications, but it might be a good idea just to remember an application that a low heat powder is good for and an application that a high heat powder is good for. So the high heat powder is the one that's exposed to an intense preheating treatment which denatures a lot of the whey proteins, and these type of powders are very good in applications where you're going to expose a reconstituted milk powder to high temperatures again. So things like evaporation and baking. So this is where a manufacturer takes the milk powder, mixes it in with water, and then is going to subject it again to a heat treatment. And they want to make sure that the powder that they're using will withstand that heat treatment. On the other hand, if we go to the low heat varieties down or up here, we see that they're particularly useful for cheese making, for example. And the reason for that, we said the other day, is that in cheese making, what we want to do is use an enzyme, namely rennet, to cleave the proteins at the surface of the casein micelle, or cut them, or remove them. And if we put a lot of denatured whey proteins at the surface of the casein micelle, the enzyme cannot access that surface as easily. So the whey proteins, in effect, block access of the enzyme to the surface of the micelle. And because cheese making relies on the enzyme hydrolyzing the proteins at the surface of the casein micelle, using a high heat variety in cheese making applications would be a very bad idea. So that's preheating. It's an example of a step that's used during the processing of milk powders to enhance the functionality of milk powders. And as I said, what happens when you're working in the dairy industry, or if you're working in a company that uses dairy ingredients, is oftentimes you have to select the appropriate heat classification for a specific application. So it's very important to know what the distinction is. So if we just go back for a second, this is the basic processing outline for milk powders. As we said, we've got some additional optional steps that can be used during the production of milk powders. The next step after preheating that always occurs is evaporation. And you did do evaporation with urea, but I might just briefly mention what happens during evaporation again. So the purpose of evaporation is to remove water, or we can also say to increase the solids content of the liquid. So the liquid enters the evaporator at roughly 10% solids, and then the solids content is increased by a factor of roughly 5. Okay? Now we'll see at the end of this lecture, or maybe at the start of the next lecture, that there's some subtle differences in how high we can go with the solids content during evaporation, depending on the precise nature of the liquid. So for example, you might not be able to push the solids as high with a high heat milk powder, okay? So if we take milk and we expose it to a very high preheat treatment, and we denature the whey proteins, we end up with a far more voluminous casein micelle structure, which entraps more water and produces a more viscous liquid, okay? So if you take that more viscous liquid and you try to push it to a solids content as high as 50%, which you might be able to achieve with a low heat system, you might struggle to evaporate that material because it's too viscous, okay? And viscosity is really important during evaporation. It causes a lot of problems. So this is the kind of zoomed out diagram of the evaporator, and what we see here is that it's an elongated structure. The milk is pumped into the top of the unit here, and inside the unit we've got these long series of vertical tubes. As we said last time, I think they're called calandria, which is an unusual word. So the milk falls inside these long tubes, and on the outside of the tubes is steam. So steam is pumped into the outer shell, and the tubes contain the milk that's falling vertically downwards through the unit. So we have milk falling down the tubes, and outside the tubes we have steam. And the heat from the steam transfers through the tubes and heats the milk that's falling downwards in a film. Another important thing to say about an evaporator is that the evaporation step is typically performed under vacuum. So a vacuum is pulled, which means that vapor can be generated from the milk at a lower temperature than would be typical. So you don't have to go as high as 100 degrees Celsius or higher in order to generate vapor from the milk. So if any of you are struggling to conceptualize how this equipment works, there's a pretty good video here. It's very short, and it shows this falling film type evaporator in action. And I've just taken some screenshots from it here. This is a picture inside one of the tubes, and we see that the liquid is flowing into the tube, and then it just forms a film on the inner walls of the tube. So if we take into account that we have many of these tubes, and in each of these tubes we only have a surface film of milk, we have a very high surface area for heating. Okay? So an evaporator is a very efficient way of removing water from the system. Now, as Uriel probably said, so this picture here is what's called a single effect evaporator. Uriel probably talked to you about multi-effect evaporators. So in this type of evaporator, the steam that heats the milk has to be generated, okay? So you have to take water in a boiler and generate the steam separately so that it can be used to heat the milk. But as Uriel probably said, in this evaporator, when you heat the milk with the steam, the milk itself generates vapor. And that vapor itself is like steam, okay? So it's a hot vapor. So that vapor that you generate from the milk can be recycled and then used as steam to evaporate more milk, okay? So oftentimes, we don't just have one of these evaporator units, we have 2, 3, 4, 5, or 6. I think as many as 6 or 7, okay? And what happens is you have the vapor that's being generated from early stages or effects being used to heat milk in later stages, okay? So you're evaporating the milk, you're generating vapor, and then you're using that vapor to heat other milk and concentrate. And in most dairy factories, I think there's about 6 or 7 effects. If you go to 8, 9, 10, you're wasting your time, you're wasting your money, okay? There's no further benefit if you increase the number of effects. So as you can imagine, intuitively, because you have a liquid falling down as a film through a very long tube and becoming increasingly more concentrated as it falls down the tube, viscosity has a very important effect. So if we have viscosity here on the y-axis, and if we have solids content on the x-axis, as the solids content increases, your viscosity also increases. And let's say if we call this low heat skim milk, so this is milk that's been exposed to a typical pasteurization temperature, and it's got micelles that look like this, so it's got the little catechaceins at the surface. This will increase in viscosity because of the increase in solids, but if we compare that to a high heat system, we might find that the viscosity increase is much more severe. Because in this system, in the high heat system where we've denatured the whey proteins, we've got something that looks like this. We've got much larger casein micelles because their surface has been extended by the whey proteins out here. And they trap more water. And the solids content that has to be reached before the casein micelles get really close and begin to interact and produce a kind of thick, viscous quality is lower. So if you've done any heating step prior to the evaporation that causes this attachment of proteins to the surface of casein micelle, you're probably going to get a system that becomes more viscous at a lower solids content. So here, if we look at this region here, the high heat system would achieve a higher viscosity at a much lower solids content than the low heat system. The consequences of this is that you might not be able to increase the solids content of the high heat system to the same extent as the low heat system, and that's less efficient, okay? The entire purpose of the evaporation step is to try to increase the solids content as much as possible before drying. And this is just one example of something that causes milk to become too viscous too early. There's actually many examples that cause this problem. Okay. Another one to think about is if you were evaporating whole milk versus skim milk. Which do you think would become more viscous during evaporation? Skim milk. Why? What's your reason? In skim milk? The milk fat globule membrane will protect the caseoid or the... Okay, interesting. I wouldn't have thought about it that way. I would think of it just much more intuitively, like if you buy whole milk in the shop and if you buy skim milk, which is better? Like which tastes better, or which is more pleasant? Whole milk. Why? Yeah, what does that do?
More creamy.
It's creamier. So because of the presence of the fat globules, which are particles which contribute viscosity, whole milk is more viscous. And as you concentrate it, as you evaporate it, it remains more viscous all the way through this curve. It's always more viscous than the skim milk. So if you've got denatured proteins, if you've got fat globules, you've got more viscosity, you probably can't increase the solids content to the same extent in the evaporator. Okay? That's something that's very practically important when you're producing these powders. Another thing you spend probably a lot of time talking to Yuri about is spray dryers. Okay? So the vast majority of milk powders are produced by spray drying. Now you should make a note at this point that not every milk powder is produced by spray drying. And we'll give an example of alternative drying technology in a second. So this is called, just like evaporators can come in multiple stages. And spray dryers can also come in multiple stages. And the example that's shown up here, you've probably seen or may have seen during practicals with Dave Waldron. This is a single stage dryer that we actually have in a pilot plant in UCC. Now single stage dryers are typically found in pilot plants. Okay? They're very rarely actually used to produce commercial scale milk powder. Okay? They're typically used for research projects. Okay? So many of you, if you're going to work for an ingredients manufacturer, you'll see that they have spray dryers that are multiple stories tall in their factories. And then they've got these small little spray dryers in their pilot plants. And if they're coming up with a new experimental ingredient idea, they'll first test it on this type of spray dryer before they go to the big one. Okay? So these single stage spray dryers are typically for research and development purposes. And what we have is a big chamber. We have a big chamber here where the drying occurs. And the milk is pumped to the top of the chamber, and it's pumped at a very high velocity through a very small nozzle. And in the nozzle, the milk forms a spray, or an atomized spray, with a very, very high surface area. And because there's a very high surface area, when it's exposed to hot air, the moisture is removed from the droplets very quickly. So we form an atomized cloud or spray of milk, concentrated milk, and the milk droplets begin to fall through the chamber. And as they're falling through the chamber, they're exposed to hot air. And the milk droplets begin to lose moisture, and eventually they transform into powder particles. And in a single stage spray dryer, when the particles are removed from the main chamber, they should have a moisture content of about 5%. So you should produce a very dry powder using a single stage spray dryer like this. So the temperature at the top when the milk enters the chamber, the temperature can be as high as 180 degrees Celsius or 200 degrees Celsius. Very high, okay? And that's called the inlet temperature. So where the milk enters the chamber, the temperature is really high. And this actually, some of you may have seen in the last few years, there's a nutritional scientist from Brazil, one of them is called Monteiro, and they're very concerned with what they call ultra-processing of foods. So they've started classifying foods based on their degree of processing, okay? So typically foods in a nutritional context are classified in terms of how many vitamins they contain, how much protein they contain, how many calories they contain. But these nutritional scientists are saying, no, what we really think about is the degree of processing. So some things are more processed than others, and we need to look at how these foods are processed and start to try to eliminate processed foods from our diets. Okay? So it's kind of changing the focus in a nutritional context. And this system they've developed, it's called a NOVA classification. You should look it up. Most of the papers are freely available. They classify foods that have been spray dried as being ultra processed. And one of the things they refer to is that they say, in these spray drying process, they're exposed to temperatures as high as 200 degrees Celsius. This is terrible. We all know that really high temperatures can, damage nutritional content of food. But because they're nutritional scientists and not food scientists, they don't know that the milk material here in this dryer, and any food that's being spray dried, the actual temperature the material is exposed to is about 80 degrees Celsius. Okay? So it's not as high as 200. Does anyone have a reason for that? Evaporative cooling. So just like when you're sweating, you form a very thin film of sweat at the surface of your skin. The sweat evaporates and cools you. That's the biological function of sweating. When the droplets are falling through this chamber, they lose moisture very rapidly and then cool very rapidly. So the nutrients inside in the powders are not really exposed to a temperature as high as 200 degrees Celsius. It's actually far lower than that. And this is one of the reasons why spray drying is as popular as it is. Spray drying is actually very gentle on nutrients. And it's very gentle on bacteria. So if you wanted to spray dry a probiotic, for example, and make sure that it remains active, you can do that by spray drying, okay? So the other type of drying we're going to see in a minute or two, roller drying, that was originally used, roller drying, for things like infant formula. But they found that the temperature increase was so high during roller drying that it negatively impacted the nutritional profile of infant formula. So eventually, they switched to using spray dryers because the particles or the droplets just are simply not exposed to temperatures that are high enough to cause significant nutritional degradation. Okay, so this is single stage drying. The only stage of drying that happens is in this drying chamber. So we have droplets falling through the chamber and transforming into dry powder particles with a moisture content of about 5%. Then we have two-stage dryers, and in the chamber of a two-stage dryer, we have the same thing happening, except the powder typically isn't as dried, or isn't dried to its final moisture content in this first stage of drying. So by the time the powder leaves the main chamber, it might have a moisture content of 10% rather than 5%. And then the powder exits the main chamber and it is transferred to a fluidized bed. So a fluidized bed is a perforated screen through which hot air is blown through. So here we have hot air being blown through the perforated screen. And the hot air causes the particles to, in effect, levitate, okay? So the particles start floating through the perforated screen. So the hot air does two things. It removes further moisture from the particles, but it also moves the powder through the dryer. So it fluidizes them. The particles, even though they're solid particles, act almost like a liquid. They're moved through the dryer. And as they move through the dryer, they reduce from a moisture content of 10% to about 5%. So in the first section we have hot air. The hot air does two things. It dries the powder, but it also fluidizes it or moves it through the dryer. And in the final stage, instead of hot air, we have cool air. And the cool air obviously reduces the temperature of the powder so that it can be packed. And finally, we have a three-stage dryer, and this is often called a multi-stage dryer. So even though the two-stage dryer here also has multiple drying stages, typically when we talk about a multi-stage dryer, we're talking about a three-stage dryer. And this example is very similar to the previous one. We have a chamber, main drying chamber, we have an atomized cloud of milk concentrate, the droplets fall through the chamber, they lose moisture, and ultimately the drying is finished in an external fluidized bed outside here. The main difference is that we also have what's called an internal fluidized bed. So what happens here is particles that have transformed from droplets and descended to the bottom of the drying chamber are then actually blown using hot air back into the main chamber. Okay? So we have particles being recycled back into the main chamber. And one of the important effects this causes is it promotes agglomeration. So what we have at this point is we have particles falling downwards, and then we have particles being transferred upwards through the chamber also. So what we have is collisions occurring between particles and droplets. So we have a particle falling down the chamber, or a droplet falling down the chamber, and then we have a particle moving up. And they collide at this point, and they form a larger particle. And then this falls down the drying chamber and dries into a large agglomerate type particle. And this has a lot of functional benefits. So agglomerated particles flow better, they solubilize better, so they have better functionality. So multi-stage dryers, again, are more common in actual manufacturing of milk powders. And they're more energy efficient. But in addition to that, they typically produce better functionality in the powder due to a promotion of this agglomeration effect. So there's a whole science to optimizing spray dryers, okay? There's experts that just think about spray dryers, okay? Getting the temperatures right, getting the atomization pressures right, changing the type of atomizer, promoting agglomeration, endless variations of spray drying parameters. And this diagram kind of summarizes some of the main levers that an operator of a spray dryer might be able to modify in order to change the functionality of the final powder. Okay? So I've highlighted one obvious one here that has some importance. So if you increase the solids content of the concentrate going into the dryer, this has a direct impact on viscosity. So this should be somewhat obvious. If you take something viscous like honey, and if you add water to it, if you dilute honey, it becomes less viscous, it becomes more watery. On the other hand, if you take something like milk and you concentrate it by removing water, it becomes more viscous. Okay? And this is kind of hard to imagine when you're in a lecture, but I remember the first time I saw like liquid whey. It's just clear and green, like water. And then it went through an evaporator, and it was in a little milk, one of those old-fashioned stainless steel milk containers, whatever. But it was like syrup, okay? The concentrated whey was like syrup. It was gloopy, okay? Just because the solids content had increased. So if you increase the solids content, you have a much more viscous feed going into the spray dryer. And when you put something that's more viscous through the atomizer, it produces larger droplets, okay? So the more viscous the feed material for the spray dryer, the more the droplet kind of drags on the atomizer walls during atomization. And because of that, it produces larger droplets. So if the solids content changes by as little as 1%, you can have an impact on feed viscosity, which changes the size of the droplets. And if you increase the size of the droplets, you reduce the surface area, okay? So bigger droplets, lower surface area. And if you lower the surface area, you've got less efficient drying, okay? So any time we talk about increasing a surface area of something in food, we're typically increasing the rate at which something happens, either a chemical reaction or a phase change or whatever it might be. And remember, when we're producing this atomized spray of milk, we're trying to produce a very large surface area so drying will happen very efficiently. But here, if we have this slight increase in solids content, we might have an increase in droplet size, which then increases our moisture content. The consequences of that are that you're producing a milk powder, it's sent out to 12 customers in China, Argentina, Britain, wherever, and the next day there's calls from all those places saying, we measured the moisture content and it's 0.2% out of spec or something like that. So we're rejecting it. And it's a big catastrophe and everyone's stressed. If that happens, so someone comes into your office, you're a research and development person or a quality person, someone says, everyone's going crazy, the moisture content is off, people are worried about bacteria, people are worried that there might be pathogens growing in the milk powder could be going into infant formula, like it's a serious thing. Because remember, when we make these powders, one of the reasons we're reducing the moisture content is we're trying to make something that lasts longer, something that doesn't foster the growth of bacteria, okay? So this is something that's a major concern. Now, if you're a scientist working in one of these companies and someone confronts you with this, one of the first things you should be thinking, is what's the solids content going into the dryer? Has the solids content changed? Are we still evaporating to the same solids content? Has anyone measured the solids content in the last week? And you might find that the solids content has increased for some reason, and this results in an increase in droplet size due to an increased viscosity, and then we've got less efficient removal of moisture, and that might be the cause of our out of spec moisture content. Okay, so this isn't just this isn't just pointless tweaking of parameters. It can potentially be very important. And another thing that can impact moisture content is the outlet temperature. So I said the outlet temperature is much lower than the inlet temperature. The outlet temperature can be about 80 to 90 degrees Celsius, but usually it's controlled to within plus or minus 1 degree, or less. And we see here again that if we have some fluctuations in our outlet temperature, we can impact the moisture content of the final powder. So an obvious thing as well, if someone is trying to design a spray drying process and they have a goal to produce a powder that's 4.5% moisture content for whatever reason, but if they're only getting a moisture content of 5% and they don't know how to go lower, an obvious thing to change would be to increase the outlet temperature. Okay. So, when you talk about milk powders, when you're writing your first answer in the exam about powders of any type, you can say, you know, when you're taking a liquid material and you intend to produce powder, what you're doing is reducing the moisture content. Why do you reduce the moisture content? You reduce the growth of microorganisms. You reduce the rate of chemical reactions in the material. You reduce its weight so it can be exported abroad. So one of the most important things about producing a powder is that you get a moisture content that's low and within a certain range of specifications. So knowledge of the factors that influence the moisture content is really important. So these are different dryers. This is what you talked to Uriel about. And as I said, the vast majority of milk powders are produced using spray drying. Okay? But some milk powders are produced by what's called roller drying. And roller drying was actually an earlier technology than spray drying. And it's a fairly simple type of technology to visualize. So here we have a roller dryer, and we have our concentrated milk falling between these two rotating drums. So the milk here in blue is falling down between these two rotating drums. And inside these drums is some type of heating medium, which is typically steam. So the drums are heated from the inside using steam. And this results in the surface of the drums being very hot. Okay, so we have a hot surface that's rotating. The milk falls between the two drums and coats the surface of the drum. So here we have coating of, let's say, this wheel, or drum here. We have coating of the surface with this thick milk concentrate that's after coming off an evaporator, for example. And then the milk that's on the surface rolls from here to here to here to here to here, and then eventually it reaches this point here where there's a knife, okay, so a sharp blade. And the blade then cuts off the dried milk powder from the surface of the drum. So by the time the milk concentrate moves from here, which is, let's say, 2 o'clock on an analog clock, and moves to 11 o'clock, it's gone from being a concentrated liquid to a dried powder. But it's quite different to it's quite different to the situation in spray dryer where you have droplets. What you have instead is basically a cake of milk powder at the surface of the drum. So you have a you have a drum that's basically coated with a skin of dried milk powder, and then the knife cuts off that caked material from the surface. So what falls from the drum here is kind of like flakes of milk powder. Okay, so it's quite a different type of structure. And then those flakes fall down into an auger, and the milk powder is transported out of the drying system for packaging. Okay, so there's various advantages and disadvantages to roller drying. I'm not going to spend a lot of time talking about them. An obvious thing, if you just look at this, they're very small. I don't know has anyone actually seen a real spray dryer that's used in a factory before? They're frighteningly large. It's like, I don't know how to, if someone asked you to work on one of these spray dryers that they actually use, if they said go in there and use that, you'd have a panic attack. They're gigantic. They're enormous multi-story structures with a very tiny nozzle at the very top. So you walk up winding stairs all the way up to the top, several stories, and there's a tiny little atomizer that produces the spray. On the other hand, these roller dryers don't take up much space. And that's an advantage, because if you want to install a spray dryer in a factory, then you're going to have to build basically a massive multi-story shell around it to support the structure and allow people to access it. Whereas a roller dryer, you can just have it on one floor. Okay? So it's just, it costs less to install. and it takes up less space. Okay, so they're small, easy to install, cheap structures. But they've got disadvantages. So we said that during spray drying, we have a very low temperature that the actual molecules in the food system are exposed to. But during roller drying, the temperature that's reached inside in the food system or milk system is far higher, okay? And oftentimes, as you might be able to imagine, the mechanism by which the knife actually scrapes the material off the drum, it's imperfect, okay? So you can imagine that there's a knife, there's a knife, let's say we have a rotating drum here, and then we have some type of knife, okay? And the knife has to cut the material off the surface of the drum. So the drum is rotating, and we have a knife that has to cut the material off the surface of the drum. But if there's any imperfections in the knife, if there's any, if one part of it here is slightly higher, which will happen over time due to wearing of the equipment, then it's going to just miss the milk material here. So what will happen in that situation is that you might have milk material that passes from here to here, dries, and then just keeps rotating and rotating and rotating, and it's exposed to high temperatures for a very long time, and it'll burn and burn and burn and burn, and then eventually it will scrape off, and you'll have burnt material in your sack of powder. So that can happen. The system is very vulnerable to imperfections in the surface of the drum and the surface of the knife. And if there's imperfections, which is common, you can get scorching of particles. That's not really a risk you have in spray drying. So there's various disadvantages of roller drying, even though there is some advantages like its low space requirements. So why do people still use roller drying? So there is some companies that still use roller drying to produce whole milk powder and sometimes sodium caseinate. So we haven't started talking about sodium caseinate yet, but if you're making notes on roller drying right now, you should note that roller drying is used for whole milk powder, but also sodium caseinate. And it has functional benefits for those two powders. So we'll talk about why roller drying would be used in sodium caseinate later, but for now, note that roller drying promotes the release of free fat at the surface of the powders. So normally when you're making whole milk by spray drying, you want as little fat on the surface of the powder particles as possible. If you have fat on the surface of the powder particles, obvious bad things will happen. Like the powder won't solubilize very well because fat is hydrophobic. And normally when you produce a whole milk powder, if you look at the particle, basically what you have is a continuous matrix of lactose, a continuous sugar structure. And then embedded in that structure is little fat droplets. So when you add the powder to water, the lactose does most of the work in terms of solubilization. Typically, the solubility of whole milk powders can be quite good because you have a high concentration of lactose, and lactose is a sugar, so it's hydrophilic. Okay, so when you spray dry whole milk powder, you typically have a low free fat content on the surface, but when you roller dry it, you have a massive increase in free fat. I don't know the precise mechanism, and you don't need to know it, but something about the roller drying process forces oil to the surface of the particles, okay? And there are some applications of whole milk powders where that's a good thing, okay? And a particular application is the production of milk chocolate, okay? So milk chocolate often uses roller dried milk powders. So milk chocolate typically has two sources of fat. One is cocoa butter and one is the whole milk powder. And if you have a milk powder that has a lot of free fat in it, then you can use less cocoa butter. Okay? So you have two sources of fat. One is the whole milk powder, one is the cocoa butter. If you have a milk powder with a lot of free fat at the surface, the free fat contributes to the formation of the chocolate structure that is desired by manufacturers. Why is this important? Cocoa butter is an incredibly volatile commodity. So this is the price of cocoa butter in 2017, 2018. We can see it's kind of volatile, it goes up and down, but it's also increasing, okay? So chocolate manufacturers want to, if possible, minimize the amount of cocoa butter they use in their formulation. One of the ways you can minimize it is by using whole milk powder that has a very high free fat content. If you want milk powder with a very high free fat content, you might look for a supplier that uses roller drying, okay? If you're working in a dairy processor that doesn't have a roller dryer, you have a spray dryer, then you might be interested in optimizing the spray drying process so that you can promote the release of free fat at the surface. And that's possible. But I'm not going to go into it. Okay, so I'll leave it there. Thank you.